Now let's consider the relationship between the intensity and the flux. So flux is the net energy that passes per unit time through a unit area in a frequency range. If you compare this with the definition of intensity, then we can derive a relationship between the intensity and the flux. The integral is because both the flux and the intensities are finite quantities, and then here we have 3 infinitesimals, whereas here we have 4. So we can see here from this relationship that the flux is the directional integral of the intensity. Now for an isotropic field where the intensity does not depend on direction, and we can only see one hemisphere, then we can evaluate this integral, remembering that the infinitesimal solid angle is sine theta d theta d phi. So this integral is... Now, if the intensity is isotropic, you can take it out of the integral, and this becomes simpler. If you see the full hemisphere, then you're seeing phi 0 and phi 1 from 0 to 2 pi, and theta is going from 0 to pi over 2. So the flux is integrated in solid angle. That means that the directional information is eliminated. The intensity can only be defined for extended objects, angularly resolved, because we need to specify the interval of solid angles. Flux instead can be defined for any source, including point sources. You cannot define intensity for a point source. What defines it being a point source or not is if its angular size is smaller than the angular size of your detector. Notice that if the angle omega is small, as it usually is for astronomical sources, then this flux here becomes simpler to evaluate. It means that if theta is around 0, that means a very small source in angular size, that means cosine theta is about 1. And if the intensity is then constant in that source, then you have that the flux is about intensity times omega, where omega is the solid angle. So let's consider this problem here. A spherical star of radius big R emits radiation of intensity I in all of the directions. Now you are an observer at the distance little r, and you want to describe the radiation field, obtain the mean intensity and the flux. So this figure here shows the angles that we are going to deal with in the integration. So you are here a distance r away. You see the star has a radius big R. That means that the angles that you're seeing are up to maximum angle here, theta max. The angles that you're measuring, the phi angle that you measure is this. So this is a full 2 pi. This is an azimuthal sweep around the star. And the angle theta here, the meridional angle would be this one. So you're seeing the star up to an angle theta m. The measured intensity is thus I for meridional angles from 0 to theta m, right? These are the only angles where you see the star. And azimuthal angles from 0 to 2 pi. And the intensity is 0 for the theta angles beyond the theta m to 180. And again, from azimuthal angles from 0 to 2 pi. So this is the radiation field. I nu is equal to I nu for theta from 0 to theta m, and phi from 0 to 2 pi, and 0 for the other angles. Where theta m is given by the figure here is the arc sine of big R over little r. Now the problem also asks for the mean intensity. The mean intensity is the directional integral of the intensity. So this integral becomes I over 4 pi. And what is changing are the limits of integration. Phi is going from 0 to 2 pi, but theta is going from 0 to theta max. The integral sign is minus cosine, so this yields I over 2 over 1 minus cosine of theta m. As for the flux, is the integral of the intensity in cosine and solid angle. Again, apply the limits. Now this integral gives you sine squared over 2. So substitute in the definition of theta m, and you recover the 1 over r squared dependency on the distance.